on this page, what we see is variable oxidation state. Okay, so just now they already mentioned it has variable oxidation states because the energy difference between 4s and 3d are small. So you can see here, small energy difference between 4s and 3d. So electron from both subshells can be removed to form a variety of oxidation states, like vanadium, can be +2, +3, +4, +5. So because of small energy difference. All transitions metal exhibit 2 or more oxidation states. So that is the one of the special properties of transition metal. It exhibit more than one oxidation state. So which means 2 or more oxidation state. Not like not like group 2. The oxidation state is always +2. Then group 1, the oxidation state is always +1. Only one type of oxidation state for those group 1 and group 2. But transition metal, there can be more than that. Okay, more than that. It can be 2 or more. Like vanadium can do +2, +3, +4, +5. They can exhibit 5 oxidation states. So next point, most common oxidation state is +2. Reason, because 2 electrons from 4s. 2 electrons from 4s lost. So that's form +2. +2 when you remove 2 electrons from 4s orbital. Next point, transition elements show highest oxidation state when they combine with oxygen or fluorine. Oxygen and fluorine. Okay, so example you can see here, CrO4 minus. If you go and count the oxidation number for chromium, so of course we count it in this way, chromium O4 minus. So you don't know the oxidation state, let's say, but you have to know the oxidation state for oxide here. The oxide here is -2, 4 of them. So the overall charge is -1. Okay, so over here, if you go and count it, then you will get -8, bring over, become +8, +7, So, which means what? Which means chromium is taking a high oxidation state of +7. Okay, +7. So in this case, right, what I can say here is when they form high oxidation state, they have to combine with oxygen of fluorine to make themselves more stable. If they remain alone as chromium 7 plus, it is too positive and not stable. You imagine the negative ion can quickly come and combine with it. So because of that, it is not stable if they are alone. So they need to combine with oxygen of fluorine to stabilize themselves. And because of that, you see next point, I said, when transition elements form compound with high oxidation states above +4, they form large oxo anions. That means they form anions that combine with oxygen. That is the oxo. Oxygen is there. And are covalent acidic oxides. They are covalent. So meaning that the oxygens form covalent bond with chromium. They form covalent bond. Okay, so and they form covalent bond, and covalent is normally acidic one. So that's why when they form covalent bond, it end up with they are acidic. Their properties is acidic here. So we have these two as the example. Okay, now These are called oxo anion. Next point, when transition elements in lower oxidation state, they form ionic compound. They form ionic compound. And ionic compound is basic oxide. Basic oxide. So, example, low oxidation state, copper 2 chloride. So this is basic. Okay, copper 2. Since they say oxide, so I put another example, copper 2 oxide. So again, this is ionic. Copper 2 oxide, I think you know this is ionic long time ago. So yes, they are ionic. And at the same time, they are basic. They are basic. So ionic is normally showing basic properties. So in general, it is like that. Now, let's move on. Beside forming oxo anions, okay, so they form complex also. They form complex ions or complex species. Okay, so in general, we just call it complex. So they form complex. Transition elements form complex. So what is complex here? So complex is an ion or molecule formed by a central metal atom or ion. So the central metal is the transition metal, of course. It's the transition metal. The transition metal can be atom or can be ions, and it's surrounded by one or more ligands. So we have ligand. So basically, complex consists of two parts. The first part is the central metal. This is the first part. The second part is ligand, number 2. So it has two important structures that form complex. Okay, now let us see more information. Now you know there are two components that form complex. And now let's see the next point. They said a complex consists of central transition metal ions, which is positively charged and that can accept electrons. So they can accept electron basically because it has empty orbitals. Then they can accept electron. They can accept lone pair actually. Lone pair. Who donate lone pair? Ligand. Ligand donate lone pair. So ligand is they say here negative. So not necessary or not compulsory to be negative. It can be neutral. The main thing is ligand must have lone pair of electrons. Lone pair is the main thing. So they say a species that contains a lone pair of electrons, and this lone pair will form a dative bond to a central metal atom or ions. So that is the idea of a complex. It has a central transition metal in the middle, and it has ligand that donate lone pair to the central transition metal. Okay, so let's say example. So I put one example here. FeH2O 6 2 plus. So this is the central metal or central transition metal, and the H2O is the ligand. H2O, as you know, right? H2O has lone pair. The oxygen has lone pair, and that lone pair can form dative bond with iron, with Fe. Okay, can form dative bond with Fe. And Fe, right? Fe has empty orbitals. Fe has empty orbitals. So how to see that? Let's say if you look at the first page just now, where I just write down here, Fe, right, is argon 3d6 4s2. 3d6 4s2. So when they form Fe2 plus, so you should expect Ar 3d6. So 2 electrons are removed from the 4s orbitals. So it forms 3d6. So where is the empty orbitals coming from? So imagine the 3d orbitals with 5 empty orbitals, 4s with 1. The next one is 4p. 4p, there are 3. Okay, and you have to put all the 6 electrons you squeeze together in 3 orbitals here. Okay, so in that case, you should be able to imagine there are 6 empty orbitals remain. 1, 2, 3, 4, 5, 6. 6 empty orbitals. 2 from 3d, 1 from 4s, and 3 from 4p. So there are 6 empty orbitals here. So each empty orbital accommodate 1 lone pair from H2O. So imagine H2O has 2 lone pair. As you can see the drawing here, 2 lone pair. It uses one of the lone pair and do dative bond in this empty orbital. So the second H2O molecule do dative bond here, and the third H2O dative bond here, the fourth one here, the fifth one, and the sixth one. So altogether, there are 6 H2O that form 6 dative bond with Fe. And they do it because there are 6 empty orbitals over there. Okay, so at the end, they form complex. So it has the structures of octahedra, if you still remember your AS, something like this. 4 on the square planar, and 1 more on top, another one at the bottom. So altogether, there are 6 of them forming the complex ion. Okay, so like that. That is complex. Now, we look at the next point in the notes here, coordination number. Number of coordinate or dative bond to the central metal atoms or ion. So how many dative bond? Let's say, for example, this again. 6 dative bond. So the coordination number for this is 6. Okay, next one. Different metal ions show different coordination number with same ligand. Okay, so that means you don't always expect they form 6. They form coordination number of 6. They can form others. Let's say example. Silver can form 2 dative bond with ammonia. But so of course the silver here is the central metal, and the ammonia there is the ligand. Okay, so when it comes to cobalt, so ammonia, 6 of them. So from here, the idea is you have the same ligand, which is ammonia, but although they have the same ligand, but when the transitions metal is different, so it will end up with different number of ligands that can form complex with it. It depends on the empty orbital available, of course. Okay, so and it depends on the stability of the complex. Okay, so that's why it has different number of ligand. Okay, six is maximum lah. Just for your information, 6 is maximum. They cannot take more than 6 because no space to take ligand number 7. So no space ready. It is due to space problem. We call it steric factor. Okay? Steric factor. So maximum 6. Now next one. Transition metals form complexes because ions are small in size, so they have a strong electric field around them which attract electron-rich ligand. So that means what? That means imagine Fe2 plus. Fe2 plus. They are having a small size. Okay, a small size, and the charge is 2 plus, so they can easily attract the ligand. Ligand has lone pair. So of course, lone pair means negative, negative. So the 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 transition metal which is positive attract the ligand which is negative. So they form complex. They have empty 4s and 4p orbitals. As you can see, I drew out here 4s 4p. Sometimes you have 3d as well. That are hybridized and can accept electrons. How they hybridize, we don't care first because this is university syllabus. So let's move on. Okay, the next one. This side, 5.6 ligands. So we have monodentate ligands. Mono means one. So what is meant by one here is one coordinate bond. One coordinate bond. So monodentate ligands, they form only one coordinate bond with central metal ions. Donate one pair of electrons. So just now in my example, right, I already give this monodentate ligand. H2O is the monodentate ligand. You can see H2O has 2 lone pairs, but at the end, they are still monodentate because only one lone pair is used to form one coordinate bond or one dative bond. So we call it monodentate ligand. So it is in the table, which is here. It is neutral ligands. H2O is here. Ammonia, I show you also just now in the notes. Ammonia is also monodentate. The lone pair is at the nitrogen, of course. Carbonyl. So carbonyl is also a neutral ligand, CO. Okay, so this is neutral, and most of the ligands are anions, which means they are negatively charged. We have halides. So you have to imagine they have lone pair. Sulfides have lone pair. NO2, 2 minus nitrite, hydroxide, cyanide, thiocyanide. Okay, so all these are monodentate ligand, which means they use one lone pair to form one coordinate bond. They may have more than one lone pair, but they only use one. They only use one lone pair and form one dative bond. Okay, that is monodentate. Now, what is bidentate? Then bi means two, They have they form two dative bonds, or they form two coordinate bonds. Okay, form two coordinate bonds with central metal ions. So they donate two pair of electrons, per molecule. So for example, this is the bidentate ligands. Okay, so the lone pair is somewhere in nitrogen here. So one lone pair. Okay, so one lone pair is here. You can see the red dot, and the second lone pair is there. Okay, so one lone pair and two lone pair, and you can see how they form bidentate, like how they form two coordinate bond. So this nitrogen with the lone pair donate the lone pair to the central transition metal, and this is another lone pair. So there are two dative bonds for one molecule. So what structures is this? This is ethylene diamine. Ethylene diamine. Okay, En. This is the short form. En. It is neutral. It's neutral. So this is bidentate ligand. We have another example here. This is also another bidentate ligand. So this oxygen has lone pair. So I just mark it down. The lone pair is the oxygens with the negative charge. So they will donate the lone pair to the central transition metal. So we call it oxalic ions. Oxalic ion. Okay, so it is a carboxylic acid if you can see it. Originally it is COOH on the left and COOH on the right. So it is like carboxylate on the left and carboxylate on the right. We call it bicarboxylate. So they donate the hydrogens away, then they call it oxalic ions. So it's a bidentate ion or bidentate ligand, and it is negatively charged. So now we have polydentate ligands. So the poly here means form two or more. So that means bidentate is also poly. No? It's also a poly because it includes two also or more. Okay, so more means how many? Okay, it can take up to 6, So this is the example. Ethylene diamine tetraacetic acid. CH2, and diamine, right? So you see the name is same, more or less same with this one. Ethylene means 2 carbon. So you can see 2 carbon here. Diamine means NH2 on both sides. So it's here and here. That's the diamine. But the hydrogen gone already because they want to form new covalent bond with 4 of the acetic acid. Acetic acid is what acid? It's actually ethanoic acid. Ethanoic acid. As you can see, this is like 2 carbon. 2 carbon, and COOH there. So this is like ethanoic acid. So acetic acid. So I explain the structures. So ethylene diamine is in the middle. Tetra means 4. 1, 2, 3, 4. 4 of these, which is ethanoic acid. So they call it acetic acid here. So EDTA. You can put EDTA at the abstract in exam. EDTA. So E stands for ethylene, D stands for diamine or diamine, T stands for tetra, A stands for acetic acid. So you can see 6 lone pair here. 1, 2, 3, 4, 5, 6. And they form 6 dative bond with the central transitions metal in this way. So 2 up and down and 4 from the square here. So form 6 coordinate bonds, 4 from oxygen, which is this, and that, 4 of them, and 2 from nitrogen, which is these 2. So 2 from nitrogen. So We have finished up the ligand part.